Stephen Lewis, so I'm not going to take very much of your time. I'd like to welcome everyone in the room and also our listeners online to the latest in the series of Open STEM Talks. My name, for those of you that haven't heard me say this about 100 times already at these previously, is Sally Jordan. I'm Professor of Physics Education and Head of the School of Physical Sciences. It's actually a particular joy to welcome Stephen today, Stephen Lewis, because he's, the publicity says that he's Deputy Head of School of Physical Sciences. He's actually been doing that with me through being Deputy Head of Department, Deputy Head of School for quite a number of years, and is actually standing down within the next few months, so it's great that Stephen's here today. Stephen is also, and more relevant for this talk, Professor of Atmospheric Physics. He's going to talk in a few minutes about a blue planet to a frozen desert, exploring the environments of Venus, Earth and Mars. I think there's two things I want to say about it. I said I wasn't going to say anything in introduction because he can do it himself. But the two things I would say are that I think, as you're aware, some of this is the science behind the Planets TV series, which was shown on BBC Two earlier in the year. The other thing, I was really delighted in Stephen's blurb that he says that he discusses the role played by the weather and climate on each planet. I'm pleased about that because I never know quite how to describe the science that Stephen does. So I have this tendency to say that he's a weather forecaster, but on other planets. So that's my simplistic way, which is now going to put completely right. Before we hand over to Stephen, I just want to draw your attention to several more of the Open STEM talks, which are all taking place during 2019. And the reason for that is, as you'll be aware, it's the Open University's 50th anniversary. And the details of the talks are all on the OU's 50th birthday website, OU STEM's Facebook and Twitter accounts. And because I'm also going to mention a couple of other events that are wearing different badges, if you like, the easiest way of finding all the events that sort of sit together is if you Google Open University School of Physical Sciences, and under the events page, there's more of them there. I'm just going to flag a couple of the forthcoming events. The first one, which you've had a flyer about, is that we're really honoured to have Professor Jocelyn Bell-Burnell, who discovered pulsars back in 1967 and was actually then a member of the Open University staff for around 25 years, I think. And she's going to talk about an accidental discovery, and that is on Wednesday, the 23rd of October. Then on Wednesday, the 6th of November, at 6 o'clock, Jocelyn's talk is slightly earlier, by the way, it's 5:30. We have three random people, the first one of whom is called Sally Jordan. The other two are Clem Herman and Carol Morris, and we're talking about our unconventional careers, which have led us to be three of the female professors in the STEM faculty. And the other upcoming two talks I just want to mention is that in the evening of the 14th of November, we have Dave sitting down here and Carol Haswell, who actually gave the Institute of Physics lecture earlier this week, both giving their inaugural lectures, and that's back here in this lecture theatre. And then just before that, on the 12th of November, and again there's flyers downstairs, we have Dr. Ulrich Kolb, who's giving a talk on gravitational wave astronomy, revealing the fatal end of a wild cosmic dance, which sounds lovely. So that's just to whet your appetite for some of the things that are coming in the next month, really. So do look on our website if you're interested. The boring bit, we're not expecting a fire drill this evening, so if it does go off, if the arms go off, get out. The exits are the way you came in and then up behind you, up the back there. And the fire assembly point is the car park right in front of the Bell building where you came in. The second thing is just a reminder that this talk is live online. So during the question and answer session at the end, if you're in the room and have got a question, can you please wait for the microphone to come to you, because otherwise the online audience won't hear the question. And then for those of you in the room, sorry folks online, for those of you in the room, we invite you downstairs afterwards, back down to the Beryl Cafe for drinks and nibbles. And I'm going to stop talking and hand over to Professor Stephen Lewis.
Thank you. So I was asked to speak about something to do with the planets. So about 2 years ago, I was given a proposal. One of the more interesting bits of our job is that we occasionally get these proposals to be a nominated academic, which means we're involved with the BBC co-production. Some of them don't happen. This one clearly was going to, and it was about the planets. So of course I said yes. They're a fantastic thing to be involved with. And I'm just going to tell you a little bit, really, tonight about the science behind this. I can't talk about all the planets, obviously, so I've picked the ones that are perhaps nearest to home, and the ones that we, in some ways, we know a bit about, but we certainly don't know all about. And the other thing I'd like to do is to highlight some research being done by graduate students at the Open University now, or in the very recent past, and to show how we're actually right now learning more about the planets, and how their work ultimately feeds into correcting the script and getting Brian Cox to say the right thing about everything except orbits. There was one mistake in the series. So the planets, well, you know what the 8 planets are. Hopefully you've got the poster. There's plenty of interesting stuff that's gone on. About every 10 years they remake a series of the planets. And so we thought a little bit about what's sort of exciting, what's new. Of course, you can't assume everyone's seen the previous series, but I had a bit of a think as well. You know, what I've actually learnt in the past 10 years? Well, much of my work in that time has been on Mars. I work on a lot of Mars missions. But actually, I thought two of the most exciting things, going back to my own PhD, we actually saw the south pole of Jupiter for the first time. We saw the poles of Jupiter from the Juno mission. This was 2 or 3 years ago. And they're fantastic. They've got all these vortices. These vortices lead a merry dance all over the poles. It was always thought when I was a graduate student that the poles of Jupiter were just boring. All the exciting thing was happening around the equator, and it was just a bit stagnant and boring up there. Far from it. It's turned out to be fascinating. I'd like to go back there one day. And the other thing that we've seen, that perhaps not relevant to my research directly, but I think is really exciting, is that we've actually seen Pluto and Charon, its moon, and MU69 most recently, in the last year. So these are objects far, far out in the solar system. Pluto's always just been a dot, a single pixel, until the last few years, really, when New Horizons has flown past them. And these bodies are far more exciting and dynamic, again, than perhaps we might have imagined. Pluto even has its own atmosphere at times. It outgasses and it freezes. But today, I had to focus on something, so I'm going to talk about Venus, Earth and Mars. These are Venus, Earth and Mars to scale. The 3 terrestrial planets. Why are they different? Why can we live on one and not the other 2? What can the others tell us about Earth? So, the first section of the talk is going to be a little bit of background. I can't unfortunately show you video from the Planet series itself, but I can show you a few stills of how we made the series. So actually we don't get to see the programmes. The actual filming with Brian Cox and so on is done in very short bursts, very late in the process. Most of the 2 years is writing scripts. We work with a few really talented script writers who write scripts. They send us the scripts. We try and fix the science or make complaints about what they've written, send it back, and there's a process. And there's storyboards. So this is a little example of a storyboard to do with the late heavy bombardment. In fact, 3 of these 4 frames appear later in actual. This is the drawing early on in the process. So how do we film the planets? The problem clearly is we've got some fantastic views from spacecraft, and that's actually what I'm going to show you in most of this talk. But a lot of the series, they wanted to have a very immediate view, a view of a lander driving around on the surface of Mars, or have you ever a spacecraft entering the atmosphere of a planet? And if you think about it, well, we don't have that filmed because we're not going to send a second spacecraft to film the first one. That would be slightly extravagant. And also, we don't, clearly, we can't film 3 billion years ago. So what do they do? Well, actually, it's kind of revealing that everything they do, of course, everything they filmed was on Earth. It's nearly all in Iceland and the Middle East and North America. When you come to the surface of Mars, this is actually Jordan. You can watch some magic happen in a second, hopefully. It will turn into Mars. So the rover appears. And if you watch very closely, I'm not sure if the screen's quite bright enough. Look around this area, you can actually see some scrubby little plants. There's 3 of them. Every single frame had to be processed in this way. So around here, there's 3 little plants, and all the plants disappear. So painstaking work. Similarly, this is a beach in Iceland. It's a beach near the small town of Vik, which has black volcanic sand. If you ever go to Iceland, chances are you go on a little tour around the Golden Circle, I think they call it, from Reykjavik. In fact, I've been to this beach with my wife, and it's a lovely beach, but it's black volcanic sand. And again, by the power of CGI, they don't just make this stuff up from nothing. It will turn into the late heavy bombardment, including some islands with some rather exciting explosions that don't exist. Iceland, of course, is a great place to pretend to be another planet because it's so young. And then a final example, Dentifoss waterfall in Iceland, another tourist spot you might visit. With the addition of some fake volcanoes, turns into Mars 3 billion years ago. So they're actually filming live footage and then transforming it to make the other planets. But now let's get back to something real. So one of the sort of debates we had were, so for example, in this picture, this is Mars during the Noachian period, the early part of the solar system. And they would do things like they'd put, this is the Aurora Borealis on Mars, back when it had a magnetic field, a strong magnetic field. And so they'd stick one that looked like the Earth on it. Well, that's not right, because our Aurora is green because the atmosphere is oxygen and nitrogen. Mars has a carbon dioxide atmosphere, so we had to think about what colour it should really have been, and this is the sort of advice we had to give them, and I'd like to show you some more. So, what about atmospheres? Why are atmospheres so interesting? Well, I think this is a lovely picture. It's the Earth's atmosphere. It actually was taken in 2010. It's one of the last flights of the space shuttle. It's the Space Shuttle Endeavour. This is actually a photograph that's been taken out of the International Space Station, and although it doesn't look like it, Endeavour is coming towards the space station. They're about to meet to dock. So this is before it docked. The horizon you can see just around here is actually the South Pacific and South America. I think it's Chile down there. But you get a lovely slice of the atmosphere. So the perspective fools you slightly. The space shuttle is about 300 kilometres above the surface. But this is the atmosphere, and this orange part of the atmosphere, up to about this line, is called the troposphere. The lowest part of the atmosphere, tropo means turning in Greek, tropos. It's the part of the atmosphere that turns around. It's where we live. It's where everything lives, except the deep ocean. It's only about, at its highest, 15 kilometres, maybe 12 nearer the poles. So it's a really thin layer of gas. You can see the clouds within this layer. I've lost the mouse again. But really, it's a slightly sobering thought that actually all the life that we know about in the universe lives within about 10 kilometres. Perhaps a few kilometres down into the ocean, 4 or 5 maybe, and a few kilometres up into the air, and that's it. We live in a very thin skin, thinner than the skin of an apple. The white region is the stratosphere. You probably know about this from ozone. That's where the ozone layer is, or the protective ozone layer. And the blue is the thermosphere. And by the time it goes dark, you're about 80 or 100 kilometres above the surface. So actually, another sort of sobering thought perhaps is that space is about the same distance as central London from where you are now. It's not far. Why are we interested in atmospheres? Well, I kind of had a little think about motivation. Why do I do this? And what do I do? And why does it fall into different categories? And what I came up with this time was everything has to be threes. I came up with three sort of topics. Sort of exploration. We all know weather forecasts are important. They're important for all of us, actually. I once ran a weather course here, and we couldn't think of anybody who wasn't affected by a weather forecast. Even nuclear submariners have special weather forecasts for when they come up. Certainly spacecraft have to worry about weather. I'll show you about some weather on different planets and how that affects them. Discovery, science, if you like. How do planets work? Why are they different? Is there really life anywhere else? These sort of questions, you need to understand atmospheres to answer. And then environment, finally. I've kind of shown you how we can look at other planets through our knowledge, through our experience of the Earth. Places on the Earth look like other planets when you just change the light a bit, as I showed you. But actually, maybe we can understand the Earth much better if we actually look at other planets. I think going to other planets is very good value for money. There are many, many Earth missions, and of course they're very important. But a few missions to other planets gives you context. In science, you like to change things and do experiments. We don't really want to do an experiment in this 10-kilometre layer in which we live. We probably ought to go and look at other places to compare them, to really think about how well we understand it. So the first topic, exploration. Well, some of the science I do to do with this is actually, literally, this is the nearest I ever get to doing a weather forecast. Weather forecasting is regarded as the sort of engineering to the atmospheric sciences. Here I literally have done weather or climate forecasts, and in fact one of them I performed was for this mission, this is a cartoon of Curiosity, you will call it, which is on Mars now. It landed in July 2012. I may slip into calling it MSL, which is Mars Science Laboratory, which is this boring name that scientists always use. It was called Curiosity very late in the day by a school child. NASA run these competitions. But anyway, so this is how Curiosity landed. It was a very difficult landing. The spacecraft weighed over 1.5 tons. And so we had to understand a lot about the atmosphere, how dense it is. The problem, actually, when you're landing on Mars, is stopping when you get there. It's not flying there fast enough. You're going so fast, you're going about 21,000 kilometres an hour when you hit the top of the atmosphere. And you've got to stop in 6 minutes. And you've got to stop at the right height. As we've discovered, it's not so easy. So how do we do weather forecasts? Well, actually, we have, at the Open University, we have a Mars, I've called it a GCM, that means a global circulation model. It's a big weather or climate model, if you like. And this is run by me and many of my students and colleagues. And we can run it, if you like, at a sort of coarse resolution, which we sometimes call a climate model, the sort of model that you'll run for many years, hundreds of years, to get long-term statistics. We can turn the resolution up. You might think of that as a weather forecast model. You want to forecast the weather tens of days ahead, or, well, you actually can do that on Mars, you can't do that on Earth. But we can turn up the resolution and see things. And then we can go zoom right in, and this is called a mesoscale model. Then this is embedded, they're nested within each other. And this mesoscale model on the right, this is actually the one that we used for MSL, for Curiosity. And this is Gale Crater, where Curiosity landed. You may see a little black square just there. That's where Curiosity landed, or was planned to land. And it did land where it was planned, within a few kilometres. In the middle, the yellow thing is Mount Sharp. And we've played a similar game for, well, it's not a game, it's a very serious game, for other missions. And this is some work done by an ex-graduate student of mine called Rhian Chapman. I got her to do a very similar thing, and she made a sort of fun weather forecast for Mars. This is actually for ExoMars, the European mission. And it gives you an idea of what Mars is like. She's done a sort of little graphic. I can assure you there's going to be no rain on this day. This is the day that we were going to get landings. We didn't bother to record rain. We thought that dust would be fairly medium in the morning, probably quite low in the afternoon. Something you might notice is the rather startling range of temperatures. In the middle of the day, about 1 or 2 o'clock, you've got around 15 degrees. Quite pleasant, really. Not so pleasant at night. It gets down to minus 80, about 6 o'clock in the morning. Mars can get a lot colder than that at the poles. This is near the equator. So it's like a desert on Earth, but like a desert to the power 10. A huge difference between day and night. So at 6 o'clock in the morning, it's minus 81. By midday, it's plus 15. So about 100 degrees between day and night. Quite difficult to cope with. So that our forecasts are used not only for landing, as in the case of the first one I showed you, we're interested in the atmosphere. Here, it's about surviving on the surface. In fact, one of the things they're most concerned about is dust, not because the dust will damage you directly, it can get into things and clog them, but mainly because actually it wipes out your power supply, it wipes out your solar panels. Curiosity uses nuclear power to overcome that problem. So discovery. This is some more projects, and I'd like to talk a bit about the sort of science of weather. I'm showing a Martian example again, but we do have a Venus model as well at the OU, and I work with colleagues on the Earth. So Martian weather, this picture you'd be familiar with, it's one I picked. It's storms in the near the North Pole of Mars. And the reason I picked it is because it's actually weather systems that you should be familiar with from Earth. So this is the Martian North Polar Cap. It's what you can see now is mainly water ice, but there's carbon dioxide ice on top of it, so it's cold. And down here, lower latitudes, it's warmer. And this causes a polar jet in the region where there's a big temperature gradient. And on this polar jet form storm systems. This swirly thing you can see, the lighter colours is dust that's been picked up into the atmosphere, which shows you things. On Earth it would be clouds. And this is a low pressure system, about the same as a low pressure system that would come over us. They're about 1,000 kilometres across. And if we were sitting on Mars, we'd be sitting around, actually it would be about here. And this would be a low pressure system coming across us. Over here, I don't know how well it comes out, as you can see it a bit, there's a very fine feature. This is a front, a weather front, but it's picked out by dust. And this over here, this puffy feature, is a dust storm. This is not a big one by Martian standards. It's about the size of France. It's still a huge dust storm by Earth standards, but a small. Actually, we would probably call this a local dust storm on Mars. They would go up to regional and global. So this is a small example. And actually, I can run my model, and a bit like a weather forecast on Earth, I can constrain my model to look like Mars. And here's an example. And this is a high-resolution model. The colours you're seeing are actually air temperature from the similar time of year. So it's spring in the North Pole. It's lit up, and it just gives you the idea that rather than being a boring planet with a cold pole and a warm equator, there's some exciting stuff going on the boundary between the two. And in particular, you can see the overturning from the low-pressure system with the warm air being brought around. And if you know your meteorology, you should recognise this as a warm sector. So this would be a low-pressure system as well. This is a warm front, and this is a cold front. And there's an occluded front extending up here, which is what's been picked out by the dust. This is classic meteorology. Looking a bit higher in the atmosphere now, I think this is up at about 30 or 50 kilometres maybe. This is an example of our model as it's become more sophisticated. This is actually a run done by a postdoctoral researcher of mine, James Holmes, and the visualisation is by another postdoc called Kailash Rajendran. And this illustrates the winds, and actually this is the polar jet stream. You may have heard the jet stream on Earth. Well, Mars has a jet stream as well. And you can see the jet stream going round, and the colours show you where we think there are water ice clouds. So the water cycle on Mars is very important. You can see there's a jet stream. It deviates. In fact, the jet stream splits right about here. And jet stream splitting is a very important feature in forecasting our winter weather on Earth. Going further, we can do something even more clever, and this is done by James Holmes when he was a PhD student with me. More research done at the OU, which shows a process called data assimilation. The details don't really matter, but the point is that on the left, you have observations of ozone in the Martian atmosphere taken from a spacecraft. And the trouble with spacecraft observations is they're all over the place. You know, the spacecraft goes around and around, and you get them where you get them. There's holes, sometimes it turns off, sometimes it doesn't actually look in regions, and they're all taken at different times. But we can combine those with our model of the Martian atmosphere. We think it's sufficiently realistic to produce what we call a reanalysis. So combining the observations of the model, a bit like fitting something, we fit a model, and so we can sort of fill in the holes, but not just by smoothing things over in a rather intelligent way. By every observation, we adjust the model, and then we can follow that air parcel around. And James, we're now producing these reanalyses of lots of species for Trace Gas Orbiter, an ExoMars mission that's ongoing at the moment. Okay, so the third topic I thought I'd mention is environment, and here's where I'll talk a little bit more if I've got time, hopefully. So, how do we understand, why can we live on one planet and not another? How can we understand the Earth in comparison? Well, if you're an alien astronomer, and if you're an exoplanet astronomer on this planet, maybe looking at another system, you tend to think things are rather simple. There's sunlight, falls on the planet, warms it up, and the planet itself also emits its own sort of radiation. It emits thermal infrared radiation at long wavelengths. So you can't see this, your eyes aren't adjusted to see it. In fact, the atmosphere is quite opaque to it, so it would be a bad idea to see in the thermal infrared because you wouldn't be able to see very far. Essentially you have short wavelength light coming from the sun, warming the planet up. Some of that's scattered back off the planet, and that's why you can see the planet at all. You're seeing sunlight that's being scattered back. But actually the planet itself is all the time emitting thermal radiation, day and night, and the two have to balance, essentially. We're going to balance the two. Otherwise the planet will continuously get warmer or colder, and it will get warmer or colder very quickly if they're even very slightly out of balance. So, can we work out how warm the planet should be? Well, Venus, Earth and Mars. So the classic thing that people talk about is Goldilocks zones. That's far too simplistic, and I hope I'm going to show you why. So, Venus, Earth and Mars are a beautiful example. Venus, 100 million kilometres from the Sun, Earth 150, Mars 228. So we've got three examples. And actually, if at the distance of the Earth from the Sun, you get about 1.37 kilowatts per square metre of solar power. To put that in context, I think an electric kettle might be somewhere between 1 and 3 kilowatts, depending on if you've got a fast boil one, it might be closer to 3. A more eco kettle might be closer to 1. So, very roughly, you've kind of got an electric kettle element all the time, every square metre hitting us from the Sun. That sort of power input. Venus has almost exactly twice that much power, simply from being closer to the Sun. And Mars has about half that much from being further away. And you might think, well, okay, that's obvious. So Earth's going to be just right, Mars too cold, Venus too warm. Actually not. Because if we do the calculation, I was going to make you do this, but I think since it's late at night, I won't. If you've got A-level physics, it shouldn't be too hard. We have to take into account that light that I talked about that was scattered back, the albedo of the planet. And actually, this number, albedo, is the fraction of light that falls on the planet that is then scattered back straight into space, so it's not absorbed. And for the Earth, it's quite a hard number to work out, but for the Earth, it's about 30%. So about 30% of the sunlight falling on the Earth doesn't get absorbed or warm anything. It's just scattered back by clouds, by ice, by deserts, all sorts of things. Mars is rather similar, slightly darker than the Earth, probably because it doesn't have so many clouds. Venus, on the other hand, is very shiny. If you ever look in the sky, you will know that Venus is a very bright object. That's because Venus backscatters about 75% of the solar radiation that hits the cloud tops. It's covered with clouds. In fact, this picture of Venus, as I'm showing you here, is out in the ultraviolet, because if I showed you one in the visible, it would just look pretty much uniform and white. And when we put that albedo factor into the calculation, we can work out at what temperature the planets would have to be to balance, for that sum I showed you before, to balance. And actually, we get some rather strange numbers. I've checked them several times. The maths isn't wrong, and the physics isn't wrong. So what's going on? Well, the Earth, it says the Earth should be at about minus 18 degrees. Seems a bit cold. And indeed it would be. We wouldn't be here if the Earth was, on average, minus 18 degrees. Mars minus 57. Well, we know Mars is cold. Venus minus 40. So it's colder than the Earth by this calculation. We know that's not true. What are they actually? Well, quite different. The Earth's about plus 15 degrees on average, day and night on the surface. That's the comfortable temperature. That's why we're here. And that is a natural greenhouse effect from the atmosphere. Essentially, about 33 degrees of warming from the atmosphere. And you should be very glad you've got that. Mars, not quite as warming an atmosphere, but some warming. It's actually not as cold as we first guessed. Possibly minus 20 might be a reasonable average day-night temperature. And look at Venus, 464 Celsius. Sorry, a bit old-fashioned for a second there. So about 500 degrees of warming from the atmosphere. Instead of being a cold planet, Venus is like an oven. It's not even like an oven, it's hotter than your oven. Your oven's probably about 200 degrees Celsius. It can melt lead. So why are these calculations so wrong? Well, the short answer is because these planets have atmospheres, as I implied with the greenhouse effect. These temperatures are actually what an astronomer would see. If an astronomer had an infrared telescope, the Earth would look to be at minus 18, but they wouldn't be looking at the surface, they'd be looking somewhere up in the atmosphere on average, and so on. Venus, you would actually be looking at minus 40, but that would be 65 kilometres above the surface at the cloud tops. And why is this important? Well, there's a kind of story here about life, I think. As you know, water is perhaps one of the most common substance that we find that we see in three phases. There's very few things we see in three phases at typical temperatures. We can see liquid, ice and water vapour. And this is what's called a phase diagram. It's essentially, I won't go into the details too much, but we've got pressure this way and temperature this way. And you're probably familiar with the idea that water boils at 100 degrees Celsius and freezes at 0. You may have heard that if you climb a mountain, water boils at a slightly lower temperature, about 80 degrees on top of Mount Everest. And that's because the pressure gets lower, and so you go down this curve. But the freezing point of water doesn't really change. But what happens when you go further? If you go to lower and lower pressures, you eventually hit a point where water goes from freezing, from ice, to vapour almost immediately. It boils at very low temperatures. And if you go lower and lower pressure, you come to a point where you just go straight between ice and vapour and there's no liquid water. Well, I'm not an exobiologist. There are going to be many of them here soon. I'm sure you're going to get a talk from one of them. But I think the chances are that to get life, as we know it, you need a solvent liquid. And so you probably need liquid water. Water is very common in the solar system. Let's put our planets with our temperatures, our real temperatures and pressures on. Venus I can't show you because it's probably about over here. It's so hot. You're only ever going to get vapour, water vapour on Venus. You're never going to get anything else now. Earth, obviously there's a range of temperatures. This is a sort of average temperature, about 15 degrees. So we've certainly got liquid and ice, and vapour, in fact, is available. So Earth, we can have some liquid water. And look at Mars. Mars has this rather interesting, it's typically too cold to have anything but ice, but it's rather intriguing that the average surface pressure on Mars goes exactly through the triple point of water. Perhaps that's telling us something about how Mars has evolved. But typically on Mars, we're not going to get liquid water. We're going to see ice and vapour. I thought you might like to see some water, what happens at Martian pressures to water. You don't see this very often. This is an experiment. The experiment wasn't to do with water, but it was performed by an ex-colleague, Susan Conway, and this is a tank, a Mars chamber at the Open University. You need quite a big, powerful, strong chamber to get down to Mars pressures. It's quite dangerous. And the video on the right shows that we're actually looking at gully formation in sand, but that's not what's important. That's not what I'm showing you here. I'm just showing you some water that's collected in the corner of the tray. This tray is inside this chamber, and Susan has kindly filmed it on her camera phone. And what you can see is the water is actually freezing on the top. There's ice forming, and it's boiling underneath. So you've actually got bubbles of boiling water right in contact with the ice. So we're right near the triple point at this pressure. So it's kind of weird. If we leave the water there, it will take 45 minutes to disappear. We won't watch that all. But it's not happy being a liquid. It's right at the triple point. So what's special about the Earth is not me standing in front of this rather beautiful scene, but the rather lovely fact that you can see in this scene, we've got water, liquid water, we've got some nice blue ice, and we've got clouds in the air, we've got water vapour that's caused those clouds. Of course, the clouds are the droplets of water. And I did a study with many colleagues, actually, at different universities, and we tried to work out what was going on the basis of observations. Now, I'm not going to talk you through this whole thing because it's far too complicated, but this is a more complicated energy budget than that simple picture I showed you earlier, and this is why the Earth is at 15 degrees and not at minus 18 degrees. So here's the incoming solar radiation, just as I told you before. It's been averaged, in this case it's been averaged day and night and over geometric factors. Some of it's scattered back, that's the albedo, by either the clouds or by the ice, and then some's absorbed by the surface in the end, or by the atmosphere actually on the way down. But then heat escapes. But the key point here is, actually, in our simple model, we were assuming all this infrared radiation was going straight out to space. Well, it does in the end, but actually very little of it, the thickness of the arrow shows you the proportion of the radiation, very little of it just goes straight from the surface to space. You may be familiar with having a frost on a morning after a clear night. That's because more of the infrared radiation is going straight out to space. But actually most of it is reabsorbed by the atmosphere on the way up, either by gases in the atmosphere or by particulates. And it's then re-emitted back down to the surface and around it goes. And this is the natural greenhouse effect. There's some other terms which are quite hard to work out, but we think we've got this whole balance to within 0.1 watt per square metre. So that's the Earth. What about Venus? Well, it's rather startling. Actually, as I said, most of the solar radiation is scattered straight back out. Venus is a bright object in the sky by the clouds. A tiny amount, only 6.5 watts per square metre actually gets through to the surface, straight through. But then look at this, the surface that's built up and the surface is emitting 19,000 watts per square metre. It's about 19 kettles every square metre, if you like, of power. It's being emitted back up by the surface, being recaptured by the atmosphere, and being emitted back down by the thick atmosphere to the surface. And that's why Venus is so hellish. Most of the energy is just going round in a circle like this and keeping the planet at a much higher temperature. And the minus 40 temperature that we worked out is the temperature above the clouds up here, where we're balancing the incoming radiation that's being absorbed with the outgoing radiation from long wave. These are numbers from a model we ran with the graduate students. So actually, people in the past used to think Venus must be quite a nice place beneath the clouds before they really understood this properly. This is a quote from Arrhenius, a Nobel Prize-winning chemist and physicist. And he wasn't alone in thinking this by any means. It was going to be a sort of, it'd be warmer than Earth, it'd be a nice wet jungle probably. Well, sadly, what we actually saw when we got down to the surface was something different. I thought that you might enjoy these. These are historic probes. They're obviously not the originals because the originals are now destroyed. These are Venera 4 and 7 missions from Russia. Venera 4 is special. There's certainly 13 Veneras. I think there were more. Venera 4 is the first spacecraft that made an in situ measurement of another planet's atmosphere. So it's got a special place. This is Venera 4. They're basically built like cannonballs, and if you look at the armour, there's armour from here to here. You wouldn't like to build a spacecraft like this because nearly all the mass is armour. There's very few instruments inside, and yet Venera 4 was crushed. The Soviets announced that it reached the surface, but it didn't. It could only withstand about 25 atmospheres, and it was crushed on the way down. So it made some measurements on the way down, but didn't reach the surface. Venera 7 was this beast, which was designed to withstand 125 atmospheres. So it made it. The pressure on Venus's surface is about 95 atmospheres, we now know. And it survived for about, in fact, they thought it hadn't made it, but because it toppled over, but some signals were found later, and it survived for about 23 minutes. So all that armour, and you survive for about 23 minutes, gives you an idea of how bad the conditions are. And we didn't get a photo back from Venus until Venera 13. And this is the famous photo. So this is what Venus looks like. It's basaltic rock. It's volcanic. And the upper image is actually the colour as seen. And then they've tried to correct in the lower image to sort of an Earth equivalent light so that you can see what colour things are. The rocks would be a greyish basaltic rock. Not very nice, really. Not very exciting. Perhaps a a better view of Venus, in a more modern view anyway, this isn't, of course, an image of Venus. It's a combination of two different spacecrafts. It's quite nice. It's actually a combination of radar mapping from an American mission called Magellan and thermal measurements from a European mission, Venus Express, and they've combined the two, and this is a volcano on Venus. Venus is covered in volcanoes. And you can see that the volcano is hotter than its surroundings. The colours show you the heat. But Venus is not a lush jungle. It's a pretty hellish volcanic plain with some spectacularly large volcanoes. What about Mars? Well, Mars is the other way. Mars has less atmosphere than the Earth. So Venus has about 100 times more. Mars has about 100 times less, very roughly. So actually, most of the time on Mars, when it's clear, most of the radiation does kind of what our model was doing, and that's why we only had to correct it by a smaller amount. Things do get more complicated, though. So most of it goes straight down, gets absorbed by the surface, or backscattered to space, and then gets re-emitted as long wave, and some gets absorbed by the atmosphere. But things can get more complicated. There is definitely an atmosphere there. This is a nice image of Mars from Mars Express and the ESA mission, and you can see the atmosphere. This is over somewhere called the Hellas Basin in the southern hemisphere of Mars. There's a dust storm going on. Here's another example of a dust storm crossing. This is a small local storm on Mars, crossing the northern plains just from last year. This is a really small storm by Martian standards. And what happens when dust goes, and actually this is later in the year, this is June, as you can see. This is work done by Paul Streeter, one of my graduate students, using the GCM we showed earlier. And the movie just shows you a global dust storm starting. We had a spectacular global dust storm on Mars last summer in June and through to July. The colours just show you how much dust there is in the atmosphere in total. So red means dusty. You wouldn't be able to see the surface through the red. And you can just see the dust evolving. So we're studying this dust storm in great detail, and Paul has made this nice graphic, which I've adapted slightly here, which shows you how dust can work as a greenhouse as well on Mars. So when you've got a dusty atmosphere, it's colder during the day, sort of nuclear winter idea. Some more sunlight is backscattered to space by the dust, but at night, more infrared radiation is backscattered to the surface. And so actually at night it's warmer, in the day it's colder, and the average picture is rather complicated. But we think that by doing a more detailed study, the average might actually get very slightly warmer on Mars. So we can make Mars warmer with a dust storm. So another topic we talked about in the planets was how, I think Brian said, you could read the history of the solar system through the surface of Mars. And I obviously haven't got time to talk through this in detail, but I kind of like a picture rather than lots of numbers. It's kind of hard to think about what 1 billion years means. So I've made a timeline. So the sun formed here 4.6 billion years ago, and we're over here today. And what slightly gives you a scale on this is we're here, and Tyrannosaurus Rex was running around here. So this is a long time. So the dinosaurs ended about here and started about there. The first plants only appeared about here, ferns and things. We don't really know when life started on Earth, because Earth is such an active system that very little of the Earth's surface is that old. It's getting churned around, but there are some old rocks. Venus is even worse. The whole surface of Venus is resurfaced. It's controversial how often that happens, but maybe hundreds of millions of years, through some 300 to 500 million years maybe. So there's really nothing left that tells us what Venus was like in the early days of the solar system. In contrast, Mars has bits of surface that go all the way back to the Noachian or pre-Noachian. The Noachian just literally comes from the name Noachis Terra, the land of Noah. Terra, the land of Noah. It's a slight joke, maybe, if you think about what was happening then. I went through a small period of the Hesperian and the Amazonian. I'll just show you some of the stuff we can do by looking at the surface of Mars to look way back when Mars was perhaps, we think, warm and wet, and the Earth was actually pretty horrid. These are rivers. These are the oldest rivers you will ever see by a long way. These riverbeds date back more than 4 billion years. This is a photograph taken by Viking in the 1970s. There are many of these. What's interesting is that these rivers, they're what's known as dendritic, they look like roots, and that tells you that they were formed not by flooding or extreme flooding events, they were formed by precipitation, rainfall or wet snow perhaps. So we know it used to rain or snow on Mars. And these are the remnants. All over Mars you'll find these river channels in the oldest rocks. Something that I particularly liked in the program was Echus Chasma. So this is a waterfall. This is from later now in Mars. We're talking now more in Hesperian, so about 3.8 billion years ago. And this is an image. This is a real image made from a stereo camera on a spacecraft, and it shows you what Echus Chasma looks like. It's about a 4-kilometre drop from the top to bottom, and this was once a waterfall. We can see from the patterns carved in it, and indeed in the series they used the very image to make this. If you look very carefully, you can see where there's a lot of water coming down. You might just be able to match it to places in the 3D image. So this is not faking something onto Earth. This is faking something onto a 3D computer-generated image of Mars. And yet this waterfall only lasted for a few weeks. It was certainly the most extraordinary waterfall that the solar system's ever seen, to my knowledge. How do we know how much water came down? Well, this is not Echus Chasma. This is downstream from it. But these channels are huge, and they were carved by the water that flowed away from Echus Chasma in Hesperian. So you can see, it's easy to see that these, in this image, that these look like they were carved by water. And in fact, by measuring the profile of these channels, we can say how much water flowed and how fast. They're over 2 kilometres deep. They can be many kilometres wide. Finally, some student work that another of my students did, Francis Butcher, shows that even now on Mars things are happening. This is a view of a glacier, believe it or not. It's covered in dust, but this is where the glacier is, and this is the proglacial zone. And there are things called Eskers. Eskers are essentially piles of rock that are left behind where water has melted from the bottom of the glacier and flowed out through a channel. And what's fascinating about this is this shows you a sort of 3D view of the Esker on Mars, and there's an Esker in Canada to compare. What's fascinating here is that this is very young. It's so young, it's really hard to date. Thank you. These probably something like 1 million years old or 10 million years, which is old to us, but nothing on the scale of the timelines I was showing you. So this is happening now on Mars. There are glaciers forming and melting. So what's next? I'll just sort of give you a taste of what might be coming up in the next year. Well, first of all, this was meant to be this week, but there are technical reasons why I can't show you this week on Mars. These are images from a NASA mission called Mars Reconnaissance Orbiter. I've been a co-investigator on it for many years. It's been working for 10 years. It orbits Mars 12 2/3 times a day around the poles, and they build up these mosaics. You can see the strips of images as it orbits Mars. Mars rotates underneath the spacecraft. And the reason why I'm showing you images from the end of August is that Mars recently has gone round behind the sun, so we haven't been able to talk to the spacecraft. It's just come out again, and it's all still working, so that's good news, but we haven't got the latest mosaic up. But these show you what Mars is like right now. And there's 2 spots which you may see as it comes round, which there they are. The 2 white spots mark the location of the 2 active missions on the surface, one of which is Curiosity, which is still going, and you'll see some news from this the next year. It's going to be driving higher and higher up Mount Sharp. As it drives higher, it's going to a younger time on Mars. And this is InSight. I'm also working on InSight. This is a seismometer. It's a very sensitive seismometer that's been placed on the surface of Mars. And in fact, some results from this are embargoed, but will be published in the next few weeks in Nature. There is some exciting science that's going to come out of this. So it's detecting Mars quakes. It's also detecting weather, in fact, as it's so sensitive that as the low pressure systems go across the surface lifts, and it can detect these. There's also an ongoing European mission. So many of us at the Open University work on ExoMars Trace Gas Orbiter. This has been orbiting Mars since 2016. There are 4 instruments on the spacecraft, and 3 of them we work on here, including Kasei, which took this image. This is layered terrain on Mars. This shows you this is young terrain, as you might guess from the name if you have any Latin. And it's showing you layered terrain. This is climate change. And ExoMars 2020, next July, this will be launched. This is the European rover. There will be a Mars 2020, which will have a different name, but is like Curiosity from NASA. So it's NASA Mars 2020, which we've worked on the landing for a bit as well. And this is ExoMars 2020, which has the drill in front. The big cylinder next to me for scale shows you where the drill is. And it's going to land here in Oxia Planum. Interestingly, not very far from Mars Pathfinder, if you remember that from 1996. That's the blue circle on. So Mars Pathfinder landed over here in Echus Valles, and ExoMars 2020 is going to land here. And then further into the future, I'm just starting now to develop a mission with some colleagues to look at polar science on Mars. So polar science is fascinating for understanding the climate and long-term climate change. And we're looking at here in the North Pole of Mars. These are clouds, water ice clouds, and this is water ice on the surface in the polar regions. So understanding better the energy and mass balance in this region is vital to understanding the climate. What about Venus? Well, Venus, there's nothing actually very much at the moment. There's a Japanese mission. This image was taken from a European mission, and in fact you can see the contrast between the day side and the night side. The blue is images in the ultraviolet, which is how you have to look at the day side, and the red is images in the infrared, which is how you look at the night side. And the day side is so bright that you can't look at it with the same instrument that you look at the night side. Otherwise, you burn your instrument out. We will go back to Venus. On the left is a European proposal called Envision, which may or may not happen. But on the right, on the left, are some more speculative ideas. There are many proposals to fly balloons in the atmosphere of Venus, maybe for several weeks. They have to be metallized to survive, which is why they're they're shiny, so that they don't get too heated up by the sun. And eventually, even more extraordinarily, NASA have ideas to have manned missions, but we won't ever go to the surface of Venus, at least not in the near future. We will have to live above the clouds, about 70 kilometres above the surface in these airships. So finally, I'd just like to finish by showing you sunset on Mars from Curiosity. You may notice on Mars you get a blue sunset, so I'll leave that as a question for you to think about, why the sunset is blue on Mars and it's red on Earth. Thank you very much.
Okay, so do we have any questions? There's one right at the back. Megan, I think, is heading that way.
Thank you. I have a question from my daughter. Do planets have to have water, or can they have other liquid? And I don't know if I could ask a question as well, which is there any chance the Earth could end up with a really horrible atmosphere if we're not careful?
The second one first then. There's every chance the Earth will end up with a very horrible atmosphere. One day it will, undoubtedly. The sun will get bigger and brighter, and one day in the distant future, even however careful we are, whether we're long gone, it will eventually become rather more Venus-like than it is now, unfortunately. We think probably in the past Venus might have had oceans, it might have had rain, and at some point it reached a tipping point, and once all that water evaporates, water itself is a powerful greenhouse gas, and it runs. Venus has gone over a tipping point, and it's become a runaway greenhouse. It will never get back. Earth, at the moment, is not in a runaway situation. Don't worry about it happening in the next few years, but maybe in the next billion or several billion years it might happen. So we've obviously got to be careful in the near future with relatively small changes, but ultimately the Earth will become uninhabitable, yes. The first question, do all planets have water? Well, water's actually very common. It's made out of oxygen and hydrogen. It's a very common species, but no, it's not the only liquid that exists on planets. It's the only liquid that exists in a sort of comfortable temperature and pressure range. But the giant planets, for example, have exotic liquids inside. In fact, hydrogen turns into a metallic liquid inside Jupiter. The pressures are sufficiently high. But what goes on there is largely mysterious. It's way beyond what we can reach with our instruments. We've made metallic hydrogen once in the laboratory, but only once. It's very difficult to make. It's incredibly high pressure. I'm not sure that there are many other liquids. Water is the most common liquid by a long way.
Okay, down the front here, Andrew. It's Andrew.
And we'll do this one at the back afterwards. Yeah.
So, Stephen, you said how in the past Venus may have been a less horrible place. And
yes.
You said on Mars as well, liquid water would have flowed there. How long was the period of time in which Mars or Venus were kind of more habitable than they are now then?
Right, well, let's go back to my timelines. Maybe that's the easiest way. Venus, I've got a simple answer for you. No idea, because all the evidence has been destroyed. Whatever's happened, everything you see on Venus, there's nothing on Venus that is more older than a few 100 million years. So there's no reason this is why Mars, in a sense, is so special, even more special. The Earth, things get turned around. Venus is effectively like a pot that's been left to boil, develops a skin, and every now and then it just can't cope anymore, and it will overturns, and everything's destroyed. So you can speculate, we can make models, but I don't know is the answer. There's no good evidence. Of course, we know there's no liquid water on Venus now. There's very concentrated sulfuric acid in the clouds. It's a horrible place. Aside from the pressure and temperature, the rain is concentrated sulfuric acid. But the rain would never reach the surface. It would evaporate immediately. Mars, we kind of have a better idea because we can pin down quite well that the Noachian period, the Noachian period ended something like 3.8 billion years ago, and I would be happy to be corrected by several 100 million years in each direction. These things aren't that well known. These are, of course, dates that have to be made from crater counting and models of understanding how craters formed. And it then went into this period called the Hesperian that I didn't talk about so much, but the Hesperian was when it was the Echus Chasma formed. And in the Hesperian, we think it rained less. It was kind of the transition between the warm, wet Mars of the Noachian and the cold, dry Mars of the Amazonian, which started about 3 billion years ago. And in the Hesperian, there were probably megafloods, as frozen water and water trapped by ice underground would occasionally be released in vast quantities, but nothing pleasant like rainfall or oceans, unfortunately, but which might well have existed 4 billion years ago. But again, I've got to emphasise, these are vast amounts of time. I mean, a third of the age of the universe, as you know. We're talking huge amounts of time. And so there are uncertainties, but I think the evidence that Mars was once warmer and wetter than it is now is incontrovertible. Riverbeds everywhere.
There's a question
Yeah.
at the back.
Stephen, thank you. I think you've probably answered my question, that we therefore probably don't know anything about that tipping point on Venus, do we? Because there is this crazy idea that maybe it's just me that has, that whether that was self-caused by anybody on Venus, and are we mirroring the fate of Venus so many years later?
I certainly, I don't. Perhaps that was to suggest that we're going to tip ourselves into a Venus state is an extreme worry. I think we can certainly make the Earth much more unpleasant than it is now without going anything like so far as Venus. I mean, the tipping point that Venus has hit is quite different from the tipping points we talk about with global warming on Earth. So Venus has actually hit the point where the water was all evaporating. The rain no longer hit the surface, and it just went. There's no reason to think that it would have been caused by any sort of life form necessarily. I mean, Venus tipped itself as the sun became brighter. The early sun was cooler, and it's just a factor of where it is. But actually, Venus isn't so different from the Earth. It's 95% of the size. It's similar mass, and yet it's had such a different history. It's all we really know is that Venus has been unpleasant for as long as we have records, which is rather a shame because many of us are interested in it. Venus has some fascinating atmospheric dynamics, I should go and say as well. One of the really interesting things about Venus is that it rotates very slowly. It rotates in the opposite direction to the other planets. It rotates so slowly that if you walked around Venus, you could actually stay at the same local time of day all the time at just a slow walking speed. It's about 243 days, I think the year is. So it's very confusing because it goes around the wrong way, and because the day is a considerable fraction of the year, the solar day on Venus, on the other hand, is 117 days. And this gets us very confused when we model it. But it's despite the fact the planet's going around every 243 days, the atmosphere is going around every 4 days or so. It's going around about 60 times faster than the solid surface. And this is an example of superrotation. That's a very interesting problem to explain. I've worked on it several times with different students. There's no easy explanation for this. You can't take a ball of stuff and rearrange it so that the outer bit goes around 60 times faster than the inner bit. You have to invoke quite complex interactions.
There was a question there. Megan, have you got one up there? No, okay, just the one by you.
Yeah, the Earth's atmosphere is predominantly nitrogen as opposed to carbon dioxide for the other terrestrial planets. Do we know why that is, and what contribution does that make to this being a habitable planet as opposed to the other planets?
Well, the Earth has had many atmospheres over its history, actually. It probably had originally would have had almost a vaporized rock atmosphere in the early days in the Hadean, when it's gone through a steam atmosphere, undoubtedly, and it's had carbon dioxide atmospheres. If you wonder where the carbon dioxide atmosphere is, well, it's the White Cliffs of Dover, carbonate rocks. If you could vaporize all the carbonate rocks, we'd have about 100 times our current atmosphere as carbon dioxide. It's all locked up. But there's a huge carbon dioxide atmosphere here if we were crazy enough to want to release it. So the answer is the Earth had many atmospheres, and in fact, about halfway through its age, so the current oxygen atmosphere, if you like, with combination of nitrogen and oxygen, would have come about in the Great Oxygenation event, which, again, we have to argue it's difficult to pin down, but somewhere between 2 and 3 billion years ago, life forms, probably not unlike plankton in the oceans, would have started to turn CO2 into oxygen and thus doomed themselves. They poisoned themselves and enabled us to come along eventually. So things change. The atmosphere will change again.
There's a question in the middle of the room. Have we got any online? Okay, go ahead.
Thank you. 2 questions. Do we know whether the internal mechanical structure of the planets have had any bearing on the atmospheres within each of the planets and their journey? And the second question relates to the techniques that you've used to measure the weather in these planets, whether they can be applied to the moons on the outer planets in the solar system that we've been hearing so much about in recent years.
Okay, so the first question is enormous. I don't propose to try and answer it all. Of course, they do. I mean, the Venus atmosphere is undoubtedly has been outgassed through volcanoes. The Earth's atmosphere is continuously part of a really complex site. I mean, the Earth-ocean atmosphere system is a hugely complex system with exchanges between all the parts. Carbon dioxide and sulfur dioxide are emitted by volcanoes, and as many other gases, and then equally captured by rain and washed into the seas and form into rocks. So there's all sorts of cycles going on all sorts of timescales. Maybe, in fact, these cycles stopping on Mars might be the clue, I suppose, as to why. It's a vague idea. It's not a well pinned down idea. But why is Mars so close to the triple point of water? Well, maybe when the atmosphere was lost, when liquid water, if you like, finally became lost on the surface, that's when change stopped happening and it sort of sat down there. But there's no cast iron sort of theory or hypothesis around this. And do the weather measurements? Well, of course, the weather measurements we make of Mars and Venus are the same sort of instruments. Of course, they have to be adapted in various ways, but they're the same sort of instruments as are orbiting around Earth all the time at the moment. We have various climate observatories and weather satellites. We would like to put them around other planets. The problem is that to make a meaningful weather or climate measurement, you need to measure for a long time. So you really need an orbiter. It's actually quite hard to go into orbit around another body. You may have noticed many of the missions to the outer solar system fly by quickly. They fly by in a few hours and they're gone. You want to fly out that far, you want to go fast, so you get there in a space of a career. And if you're flying that fast, you've got to stop when you get there. And that's hard, because if you carry enough fuel to just fire a rocket in your direction, then you've got no mass left to carry anything interesting. So that's part of the studies we do for Mars, in fact, although it applies to other planets as well, is this aero braking or aero capture. So if you can predict the density of the atmosphere, can you dip the spacecraft into the atmosphere as it passes to help slow it down? Well, you can. We do this for Mars routinely now, but we haven't done it for anything else.
Are we going to ask the audience about the sunsets, different colours?
Oh, we've got an answer, I think.
Kath, all right. I just want to make it clear, if this answer is right, it's because the person who's answering it is the president of the Open University Students Association, and it's because of the excellent education that we provide. Is this right, Kath? Yeah, good. Go ahead. Now she'll be wrong.
Okay, so I'm thinking that you've got a thinner atmosphere on Mars, so actual scattering from atmospheric gases is going to be minimal. However, you are going to get scattering from dust, and because that's larger particles, that will scatter the longer wavelengths of red, which means that we'll see blue at sunset.
That's right. It is the dust scattering the longer wavelengths. But actually, what about Earth sunsets then? What's scattering for an Earth sunset?
I would have thought that we're looking at molecules in the atmosphere scattering the blue light.
Well, that's why the sky's blue, yes. That's why the sky's blue when you're looking away from the sun.
If we're okay, so
It's
if
actually
we're thinking at
atoms, not molecules,
sunset that we're looking at, we're seeing through more atmosphere.
It's because actually we have bigger particulates in the Earth's atmosphere, pollution and things. So that's actually, it goes the other way slightly. If you want to try this at home, we'll have a home experiment, I think. Get some water.
Have you done a risk assessment?
Oh, this is very safe. Get some water in a jar. Put the tiniest amount of milk you can. You'll almost certainly put too much in, so put a really tiny amount in and build it up gradually. And less than, the smallest drop you can do, and shine a torch through it. And you will eventually get a situation where if you look away from the beam of the torch, the jar will look blue, and if you look through the beam of the torch, the jar will look red. So you can make the sky.
I think that's probably an appropriate moment to thank you, Kath, but also, Stephen, it's been a great talk. It's been absolutely fascinating. So thank you very much indeed. And again, for the benefit of those in the room, but apologies to those who are listening online, if you'd like to join us for refreshments downstairs. So thank you very much.
Thank you.